All right, so now we're going to talk about chords of a circle and some relationships we find when we explore those. So again, I'm going to go to the Inspire and we're going to look at a few things. So in this first page of this Inspire document, I have two chords. I've got A, B, and C, D. And notice up here I've got the arc measurement. So this is 134 degrees right here. And CD, this arc CD is 97 degrees. And then over here I've got the segment length. AB is 12 centimeters, and down here I've got CD as 9.9 centimeters. So what I would find more interesting is what would happen if I make these segments the same length. So I'm going to adjust this a little bit, see if I can get them to be the same. So, okay, there you go. So this is 9.9. So 9.9 and 9.9. And notice what happened here to the arc measures. The arc measures are also the same. And that doesn't, there's nothing special about 9.9. I can also do this. I can make the arc measures be the same. So if I set that at 123, let's see if I can move this to be 123. All right, so notice I made them both 123, and then their segment lengths are 12 centimeters. So what we can conclude from that is if we have in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. And this you might have seen before when you're doing some other work. So if I know that this arc right here is 116 degrees, and these two sides, or these two arcs, I'm sorry, not arcs, chords, these two chords are congruent, that means that these arcs have to be congruent. Okay, so arc CB has to be congruent to arc CA. So we're trying to find just the measure of BC, but remember all of this adds up to be 360. So you can do it one two ways. If you want to do it algebraically, you can just label it as x since we don't know. We can say x plus 116 is equal to 360. Or some of you might just say, well, I know there's 360. I'm going to subtract off the 116, which is exactly what this equation would prompt us to do. And then you'd say, okay, I'm going to take that remainder, what's left over, and divide it into two equal parts. So I have 244 left, and I'm going to divide it into two equal parts. And that's exactly what the equation would tell us to do as well. So I don't care which way you do it. Show me how at least your thought process. So we get 122 for our x, and that's exactly what BC is, the arc BC. So 122. Okay, so that makes sense. Now we're going to go back to that Inspire and look at some other interesting things with chords. So here in this diagram, I just have one chord, and then I have this line right here, and I've constructed this so that this is perpendicular to AB. Okay, so I went from this O and perpendicular to AB, and this is where they intersect at point M. So what I'm noticing that's interesting, other than this is being perpendicular and going through the center, is that AM and MB kind of look like they would be equal to each other. So let's see if they are. So bear with me as I do some of this construction, but I'm going to measure this. So I'm going to go to my menu, go to measurement, I'm going to measure length. So I'm going to go measure from A to M. Here we go. And then I'm going to measure from M to B. Look at that. They're both 6.4. And let's see then if that's the same. Maybe this is just some special setup that makes it the same. So if I change where A and B are and how that looks, so do they always stay the same? Yeah. So you notice no matter where I put them, they always stay the same length. So what does that mean? So what would we call this line then? We would call that a perpendicular bisector, right? Since it bisects this chord into two equal parts. So, and that's true even if I were to construct this in a different way. If I were to construct the perpendicular bisector of AB, it would always go through this center point. So what we're going to write down, it's really two theorems, but they mean the same thing. So if one chord is a perpendicular bisector of another chord, then that first chord has to be the diameter. Okay, so they're just saying, oh, this has to go through the center. Okay, so that's another way of saying that. Or if we have a diameter of a circle is perpendicular to a chord, then we know that it's going to bisect that chord. Okay, so write those two theorems down, and we're going to use those in several examples. So in this example, we're trying to find the measure of PQR, that arc, and notice that we have a diameter and it's perpendicular to this chord, which means that it's going to bisect that. And so we know that since this is bisected, that these arcs would be congruent as well. So this piece and this piece would be congruent, so this would be also 40 degrees. So that whole arc, PQR, is going to be 80 degrees. Let's go back and do a little bit more exploration. So now what we have is we have two chords again. We have chord AB and we have chord CD. So, and those are those segment lengths there. So AB is 11 centimeters, CD is 8.1 centimeters. But what we also have constructed is how far away are these chords to the center. So that's what FO is talking about. FO is the distance from AB to that center O, and EO is the distance from this chord to the center. And remember, if we're talking about distance from a line to a point, we always mean that it's the perpendicular distance. So this angle at E, those are 90-degree angles. This angle at F, those are 90-degree angles. So right now, nothing matches, and it's not very interesting. But again, if I move this around so that my chords, my segment lengths are the same, so I'm going to move this to be 8.1. Notice what happened to my distances from the center. They are also the same. Okay, and there's nothing special about that. I can change these distances to be the same. So let's say I want to change E to be 2.9. So I'm going to change FO to be 2.9. And notice that AB and CD, those are both the same segment lengths. They're both 12. So again, let's write that result down in our notes. So two chords are going to be congruent if and only if they are equidistant from the center. Remember, that means that this FE and GE would be congruent. Okay, same thing as what we were just talking about. Okay, so we have two things going on with chords being congruent. If chords are congruent, we know that the arcs that they cut off are congruent, and we know the distance to the center are congruent. So here's another example. We want to solve for x. It looks like, since there's no degree measure here, 6x minus 5 is referring to the segment length ST, and then 13 plus 4x is VU. And since we see that those are both the same distance from the center, then we know that these two lengths have to be the same. So ST has to equal VU. So we're going to set those equal to each other. 6x minus 5 is equal to 13 plus 4x. So I'm going to subtract the 4x and then add the 5. And then I'm getting x is equal to 9, and that's all they wanted me to solve for. Okay, so let's look at this one. We're going to determine whether PR is a diameter of the circle. So remember, diameter has to go through the center. And here we are seeing that PR is perpendicular to this QS. So we have a chord. And we have these two arcs are congruent, which means that these two segments are congruent. And that means RP is a perpendicular bisector, so that would mean that this has to go through the center. So PR, it has to be a diameter. Over here, it's just perpendicular though. So we could have the center over here, and that wouldn't necessarily be a diameter, because we don't know, like this could be a length of, let's say, 6, and this could be 7. And if that's the case, then that's not going through the center. So PR is a diameter in this diagram, but not necessarily in diagram B. All right, so again, we will do more examples like this in class, so have your notes ready.